Hello and welcome to the third video of the M3 chapter Elastic Strings and Springs. Write down the expressions used to calculate the gravitational potential energy and kinetic energy of a particle. This is an M2 review. I hope you remember that the gravitational potential energy of a particle is given by mgh, the mass times the gravitational constant, i.e. the weight of the particle, times by the height above your zero level or below your zero level, and this was effectively work because it was force times distance, the work done against gravity. The kinetic energy of a particle was given by a half mv squared, a half times mass times the square of the speed of the particle. This one could be negative because it was all relative to your h equals 0 level, which you could choose depending on what you wanted in the question. This one, however, could not be negative. This was always positive. Kinetic energy is always a positive value. You should be familiar with these two. In this video, we're going to add a third one onto this, elastic potential energy. We're going to see how to calculate this, and in the next video, we will use it to solve problems involving these three different types of energy and the conservation of energy principle. This video is setting up for the next video, so the examples in this video are fairly simple. They're not the sort of thing you will see in an exam. Here we go. Just as raising an object by doing work against gravity stores gravitational potential energy, which is released when you then drop the object, it falls back down. Just like that, doing work to extend or compress a spring or string stores elastic potential energy. This elastic potential energy does the work necessary to return the spring back to its natural length if it's released, just like dropping an object uses the gravitational potential energy to return the object back to the ground. I have a little side note here. You should be aware of this, but it's not something that will come up in the exam. Each spring has an elastic limit, and that's just the point at which you have basically broken the string or spring. If it's stretched beyond this limit, it will not return back to its original shape or length. You shouldn't have to worry about this though, because if you go beyond the elastic limit, there's not really much left to calculate, and Hooke's law no longer applies. But just be aware that there is a limit, like when you stretch a rubber band too far and it snaps, or you stretch a spring too far and the coils start separating and it no longer bounces back. So that's a side note. The point of this video though is how do we calculate this elastic potential energy that we've got in the string or spring? We do that by calculating the work done to extend it, just like calculating gravitational potential energy, we calculate by using work done against gravity. But it's not quite as easy as gravitational potential energy, because in M2 we saw that the work done by force is given by force times distance, where we had a very simple relationship of a straight line graph like this, force here, distance here, and the work done was effectively the area under the graph here, and that was fine for moving something with a constant force, but in this situation the tension in the string or the spring increases as the distance increases. We don't have this nice straight line, it's not a constant force. We have something that looks more like this. The force here and the extension x here. As the extension increases, the force increases with it. And if I write out Hooke's law here again, we've got T is equal to lambda x over L, where the straight line graph here has a gradient lambda over L. So the work done is not as simple as multiplying the two, but if we go back to the idea of it being the area under the graph, we can see how to do this here. We've got a triangle instead of a rectangle. So the work done is the area here and here. So the work done for a spring, if we find the area of this graph here, we've got the extension x times by the tension divided by 2. So the work done is equal to tension times by x divided by 2, and knowing that the tension is equal to this, we can put that in, lambda x times x over L for this bit, and 2 combines to give lambda x squared over 2L. So the work done in stretching an elastic spring or string by extension x is this expression here. And you need to know this expression. Just like we had in the starter question, for gravitational potential energy is mgh, for kinetic energy is a half mv squared, For elastic potential energy, it is lambda x squared over 2L. So we're going to be using this in the next couple of examples, but as I said earlier, we're just building up to the more involved examples in the next video. So an elastic string has natural length 1.4 meters, modulus of elasticity 6 newtons. Find the energy stored in the string when its length is 1.6, so the extension there is 0.2 meters. The elastic potential energy, which I'll write like this, as opposed to GPE for gravitational potential energy. And just as a very quick side note, if you see me write just PE, that you can assume to be gravitational potential energy. If it's elastic potential energy, I'll always write the E. If it's gravitational potential energy, I won't always write the G. Sometimes I forget because I'm used to writing PE in M2. So the elastic potential energy here, lambda x squared over 2L, you should just get familiar with that formula. 6 times 0.2 squared over 2 times 1.4. And in this case, that gives us just 3 over 35 joules of energy. Second and final example. A light elastic spring has natural length 0.6, modulus of elasticity 10. Find the work done in compressing the spring from a length of this to a length of this. Now it's interesting here to see that it is already compressed slightly. So there is already some stored energy in this spring. All we're trying to do is find the work done to compress it further to this. So if I just find the energy in the spring at this distance, that's not quite right. I need to subtract the energy that's already there at this distance. So in this case, we're using the elastic potential energy at 0.3 meters minus the elastic potential energy at 0.5 meters. The formula, of course, lambda x squared over 2L. So at 0.3, that is 10 times 0.6 minus 0.3 is 0.3 squared over 2 times its natural length 0.6 minus 10 times 0.6 minus 0.5 is 0.1 for the extension squared divided by 2 times natural length 0.6. And I can call this the work done. And then I just calculate this. This is 3/4 and this is 1/12. So the work done is 2/3 of a joule of energy. That's it for this video, quite a short one. This is the key point. You need to remember this expression, and we're going to use that in the next video, looking at the conservation of mechanical energy. Maybe I'll see you there. In the meantime, you can practice questions from exercise 2C.